All right, howdy folks, welcome back to Professor Carbon. In this video, what we're going to do is go over an amine synthesis problem. So please, as with all of these videos, do take a second, read the problem carefully, and attempt this all on your own without the help from the video. That's a really important part of learning and internalizing some of the chemistry that we're going to be talking about. It always is easy to hear somebody else explain it. It takes a lot of dedication and effort to make a deep dive all on your own and try to internalize that information. So go ahead and pause the video now to attempt it all on your own. Okay, welcome back. In this problem, what we're attempting to do is to propose a synthesis. And I always like these because they're fairly open-ended, and as you'll be able to see, that we're going to be able to come up with more than a couple of options that could be right. And the important thing about a synthesis here is to recognize that this is a retrosynthesis arrow. So this is going to be where we start, and this is where we're going to want to end. And I know the clue here is that it's kind of a goofy arrow. It's not a normal reaction arrow. So here's our normal reaction arrows. This one is a retrosynthesis arrow. So that's conceptualizing backwards. It's telling us the starting material is here, and this is what we want to target or make. So when considering this, what I always try to do is identify some of the things that are changing. So one important thing to recognize is we're going from an alcohol to an amine. The other of which is that we need to add this CH3 group on here from the alcohol. And lastly, of course, we're going to need to put a double bond in place where there is not one currently. So all those things together can make this kind of a daunting problem. Another thing that I like to do is to think about what kind of functional groups I start with. And we've got two functional groups in the starting material, and they're both alcohols. And so that means at some point we're going to need to differentiate the two alcohols. So at some level, we're going to need to invoke chemoselectivity to get one alcohol to react instead of the other alcohol. And so that can be challenging as well, all on its own. Now, the key functional group to put in place is going to be the amine. And because we have so many reactions of alcohols, I'm going to hold off on making a list of all of those. But importantly here, we do have that nitrogen, and importantly, it is a tertiary amine. So this, in principle, would get us away from some of the problems that we might come up with either primary or secondary amines. So let's just take a quick moment down below here to review some of our favorite kind of ways to make tertiary amines. And I'm going to abbreviate it as dimethyl R. Oh, and actually, let me make that CH2R here, just for simplicity. So retrosynthetically, we could go back to having a halide, and I'll use bromide because that's my favorite halide, especially for things like SN2 reactions. And so we can imagine taking dimethylamine and displacing a halide. Remember, you always have that risk of over-alkylating with nitrogen nucleophiles, but thankfully in this case, we're making a tertiary amine, and we'd be making the tertiary amine from a secondary amine. And so we could use a slight excess of dimethylamine, and we'd probably get a very high yield of this particular reaction as long as that halide is used as the limiting reagent. And the reason for that is that alkylation of the tertiary amine to make the ammonium salt is often significantly slower than alkylating the secondary amine to making the tertiary amine. So that is okay here. We can imagine doing this through a reductive amination. And I like this one in general because it is convergent and it gives us a functional group interconversion on top of it. And just in case you're wondering, remember that this goes through an aminium ion intermediate that would then be reduced. And our favorite kind of reagent for that is going to be sodium cyanoborohydride or sodium triacetoxy borohydride. So any of those can be a great reagent for this. Lastly, we can also get to amines through reduction, and that would be through an amide reduction. And this is great here because all three of the adjacent carbons have two or more hydrogens attached to them. And so we could consider doing either of these reductions of either a formamide to reduce the carbonyl all the way down, or an regular old amide here. And what's nice about these three approaches is they're quite complementary. So if you notice that alkyl bromide, I would consider to be at the +1 oxidation state. So it's a CH2Br. The aldehyde here I would consider to be at the +2 oxidation state. And so, different oxidation state. And then over here, we would be at the +3 oxidation state. And so what's handy about this is depending on what our starting material is, we have quite a bit of flexibility for how to ultimately put that nitrogen in place. So now that we've reviewed that, let's go back and consider these two other molecules. And what I want to draw our attention to is this methyl group, because putting a carbon-carbon bond in place really limits kind of the synthetic applications that we can do. And this one is kind of in a weird spot because it's directly bound to a double bond. And there aren't that many reactions that we're aware of, at least at this stage, to just kind of put a random carbon in place. So there's two things that come to mind, one of which would be to have a Grignard reaction. So we could take a cyclohexanone and add methyl magnesium bromide to it. And then of course we need our H+ workup. And then we could dehydrate. And of course, anytime that we are dehydrating, we can always end up with a mixture of possible isomers. And remember the more substituted alkene. So this is tri-substituted. And this one is only di-substituted. And the more substituted that alkene is, the more favorable it should be. So that's okay. We should be able to have some preference there. The other thing we could do from this ketone is to, and I'm just going to put this onto the next page, is to do a Wittig reaction. So if we have PH3P, we can draw our ylide, and one of probably the most used ylides is just a simple old CH2. And so that would put this alkene in place. And because that tri-substituted alkene then is more stable, we could look at a acid catalyzed isomerization reaction. The mechanism for this would simply be to protonate that alkene, make the tertiary carbocation, and then have it eliminate in the absence of a strong nucleophile in the other direction. So you can protonate, make the carbocation forgets which alkene it came from, and then it can eliminate back on the other side. And so you can set up an alkene isomerization simply through a protonation, deprotonation sequence. So that's all pretty good. The only hiccup so far then is we don't have a great way to get to the ketone, or do we? So if I scroll all the way back up here, diol seems like a really wonderful place to start with. Now, there's going to be two syntheses that incorporate the things from below that we could talk about. So I'm just going to jot out one, and then down below, I'll kind of do the second one. So if I take this with a Jones oxidation, and so remember Jones oxidation, we're going to over-oxidize everything. And so that usually uses chromium and relatively acidic conditions, but that will take the first alcohol up to a ketone, and it'll take the second alcohol up to the carboxylic acid. Now we have what we would call a beta keto acid. I then can use something like SOCl2 or thionyl chloride to make the acid chloride. And thankfully that ketone probably won't react to in these conditions. Now I can take dimethylamine and make an amide. From this. And so that's a two-step process. In principle, we could go from the carboxylic acid all the way down here as well, just by cooking that carboxylic acid in the amine. But because the ketone also could make an imine, and then we might make an enamine, and there's a lot of other things that could go wrong. Maybe this two-step process would be more efficient. From here now, let's just do that Wittig reaction, because why not? We spent all this time learning about the Wittig reaction, might as well get some use out of it. And so this, of course, will be complicated because the H between these two functional groups is quite acidic because it can resonance delocalize. And we'll talk about that later on in the semester, but for now, let's just go with it. So give me the CH2 here. Then I'm going to use my H+. So when I use H+, my most common source of H+ here is going to be H2SO4. And then let's use lithium aluminum hydride as a very powerful reducing agent to take the amide all the way down to the amine. Oops. And for those of you that are advanced practitioners, you might recognize that because this is an alpha beta unsaturated carbonyl, there are additional complications of 1,4 reduction, but for now we will again omit those additional complications. And so this is a synthesis that uses a Wittig reaction as the key step, and the formation and reduction of the amide is a combination to put that nitrogen in place. So that works out quite nicely. All the way down below here, let's just consider a completely separate path where we start from this exact same starting material. Let's now do a selective oxidation with PCC. And what's nice about PCC, remember, is that it will stop at the aldehyde oxidation state instead of over-oxidizing. And so now we have a ketoaldehyde instead of a beta-keto acid. And so this is a slightly different combination of functional groups. According to the book, we can take these beta-keto aldehydes, and what's really nice about them is that the aldehyde functional group is inherently more reactive to forming things like hydrates and hemiacetals than the ketone is. And so we can actually get chemoselectivity to form the glycol-protected aldehyde without engaging the ketone. Now we have this protected, so now we can use the same methyl magnesium bromide I alluded to above. And so now we have our tertiary alcohol with that key extra carbon added. And now if we put this in dehydrating conditions, and this is where it gets a little bit tricky because we want to dehydrate the alcohol, but we want to hydrate the acetal. So, we might need two separate steps here, or, maybe we can find some sets of conditions to do both. But the gist is we're going to want to dehydrate the alcohol, and we're going to want to add water to the acetal. So what I'm going to put is sulfuric acid and concentrated so that it's under dehydrating conditions. And then I'm going to put H2SO4, I'm going to put dilute under there so that it's under hydrating conditions. So maybe we want to put some water in there too, just to make that explicitly clear. And so this now could give us the aldehyde back out. And then that aldehyde is set up now for the key reductive amination at the end. NaBHOAC3, so sodium triacetoxyborohydride, and that should give us a really nice reductive elimination at the end of the sequence. Now, if we have two competing synthetic pathways to consider, sometimes what we might do is either try them both and figure out which one works the best, or maybe we can see something in here that makes one pathway more desirable than the other one. So for instance, if one of them is a lot more steps, we might try the shorter pathway first. So 1, 2, 3, 4, 5, 6 steps there. And let's just go take a look up above here. 1, 2, 3, 4, 5, 6. Oh, well, at least we checked. So in this particular pathway, it looks like both sequences would be about 6 steps. Perhaps, we could shortcut that by either, trying to go directly from the acid to the amide, as I kind of had indicated, or maybe down below, we could take this and directly go to here by combining these same 2 acid catalyzed steps. In both cases, it looks like there's room for a little bit of flexibility. And what's fun about these synthetic problems is even on something this short, you can see how all of a sudden there are a lot of options and possibilities to consider. And that only gets to be more complicated as we eventually add more reactions to the list of things that are known or useful. So with that, I'm going to sign off. I'm Professor Carbon. Hopefully you enjoyed this video. Please leave us a like or subscribe. It's greatly appreciated.